Friction is a force that resists motion when two surfaces come into contact. It plays a vital role in everyday life, from walking to driving. However, in some cases, friction leads to energy loss, wear, and inefficiency in machinery and devices. Frictionless surfaces aim to minimize or eliminate this resistance by employing advanced materials and techniques. These surfaces are designed to reduce contact or create near-perfect smoothness, allowing for energy-efficient and longer-lasting systems. Magnetic levitation, Maglev, trains operate on frictionless principles by suspending the train above the track using magnetic forces, eliminating physical contact and reducing friction to nearly zero. Imagine an air hockey puck gliding effortlessly across the table. The thin layer of air beneath the puck eliminates friction, allowing it to move freely, much like how frictionless surfaces enable motion without resistance. Friction arises due to microscopic interactions between surfaces. Even smooth-looking surfaces have tiny irregularities that catch on each other, creating resistance. This resistance generates heat, energy loss, and wear. The two main types of friction are: static friction prevents motion between stationary objects. Kinetic friction resists motion between moving surfaces. Frictionless surfaces tackle these interactions by either creating smoother contact, introducing lubrication, or eliminating contact altogether. In mechanical gears, traditional surfaces experience wear due to friction over time, reducing efficiency. Replacing these with ultra-smooth or lubricated materials dramatically extends their lifespan. Think of two Velcro strips pressed together. They resist movement because of their hooks and loops. A frictionless surface would be like replacing the Velcro with polished glass, where nothing catches. There are several ways to achieve frictionless surfaces. Superlubricity involves the use of materials like graphene where atomic-level smoothness eliminates friction. Magnetic levitation lifts objects using magnetic fields, removing physical contact. Liquid layers, thin films of liquids or oils, act as lubricants to reduce friction. Surface texturing, nano-engineered surfaces create minimal contact points, reducing friction to near zero. Graphene-coated bearings in machinery provide superlubricity, reducing wear and energy loss, which is critical in aerospace and high-performance applications. It's like skiing on freshly fallen snow. The smoothness and lubrication of the snow reduce resistance, allowing for effortless motion. Frictionless motion relies on minimizing the forces that cause resistance. At the molecular level, techniques like superlubricity create conditions where atoms slide past each other with negligible interaction. In magnetic levitation, objects are suspended using repelling magnetic fields, bypassing the need for physical contact entirely. In maglev trains, powerful electromagnets generate opposing forces that lift the train off the track, allowing it to move at high speeds without the drag of friction. Analogy: imagine floating a boat on water. The water supports the boat and reduces resistance, just as magnetic forces or lubricants enable frictionless surfaces. Frictionless surfaces have the potential to revolutionize transportation. By reducing friction, vehicles and machines require less energy to move, leading to increased efficiency and reduced wear. Technologies like maglev trains and hyperloop systems rely on these principles to achieve higher speeds and lower maintenance costs. The Shanghai maglev train, one of the fastest in the world, uses magnetic levitation to achieve speeds of over 430 kilometers per hour, with minimal energy loss due to friction. Analogy: it's like using rollerblades on a smooth, ice-like surface compared to rough concrete. The reduced friction allows for faster, smoother motion with less effort. Industrial machines often suffer from wear and tear due to friction, leading to downtime and maintenance costs. Frictionless surfaces reduce wear, increase operational efficiency, and extend the life of machinery. This is especially crucial in industries like aerospace, automotive, and manufacturing. In jet engines, frictionless bearings reduce heat generation and improve energy efficiency, enabling longer flight durations and lower fuel consumption. Analogy: This is like running on a treadmill with a perfectly lubricated belt. The smooth motion reduces strain on the motor and increases its lifespan. Frictionless technology is transforming medicine by improving surgical tools, implants, and diagnostic devices. For instance, artificial joints and implants with frictionless coatings reduce wear, increasing their durability and comfort for patients. Artificial hip joints with ultra-smooth, lubricated surfaces last longer and provide smoother movement, reducing the need for replacements. Analogy: it's like replacing a squeaky, rusty hinge with a perfectly greased one. The smooth motion reduces noise and strain, just as frictionless surfaces improve joint functionality. Developing and maintaining frictionless surfaces is not without challenges. Finding materials that remain stable and durable under extreme conditions is a significant hurdle. Advanced materials like graphene or magnetic levitation systems are expensive, making the development of frictionless surfaces cost-prohibitive for widespread use. Technologies such as Maglev trains require significant energy to maintain magnetic fields, posing challenges in energy consumption and sustainability. Maintaining ultra-smooth surfaces or lubrication over time can be difficult, leading to increased maintenance efforts and costs. Graphene-based coatings are promising but expensive to scale for widespread industrial use, limiting their practical application despite their potential benefits. This is like designing a self-cleaning glass window. While it's efficient, creating and maintaining it on a large scale can be tricky and costly. The future of frictionless surfaces lies in developing more cost-effective materials and expanding their use in emerging technologies. From space exploration to renewable energy systems, frictionless designs could lead to significant advancements in efficiency and sustainability. Solar panel rotation systems with frictionless bearings could optimize the alignment of panels to the sun without wear, increasing their efficiency and lifespan. It's like using a hoverboard instead of a bicycle. Eliminating friction opens up new possibilities for movement and efficiency. Frictionless surfaces have the potential to revolutionize technology across multiple fields, from transportation and manufacturing to medicine and energy. By reducing wear and energy loss, these surfaces increase efficiency, reduce costs, and enable innovations that were previously unimaginable. The development of frictionless bearings in wind turbines reduces maintenance costs and increases energy output, making renewable energy more accessible. Frictionless surfaces are like removing all the bumps from a road. The journey becomes smoother, faster, and more efficient, transforming how we interact with technology.